Hi, this is Austin with Radical STEM Tutoring, and today we're going to find out how fast a sled can go at the bottom of a 10-meter hill with and without friction. Let's get started. Okay, so first, why don't we look at the case where there is no friction on this hill. The snow is really slick, great sledding conditions, we're going to gain a ton of speed. So with no friction, that means that we can conserve all of our energy. That is, all of our energy that we have at the top will be converted into energy at the bottom. Now at the top, if we're not moving, all we have is gravitational potential energy. And that is equal to our mass times gravity times the height that we're at. Down here at the bottom, once we're in motion and we're at a height of 0 meters, all we'll have is kinetic energy of motion. And that is equal to 1/2 mass times our velocity squared. So when we conserve energy, what we're basically saying is that we always have the same total amount of energy. It only changes forms. I usually like to draw this with a bar graph. So at the beginning, we would say that all of our energy is in the potential energy column, but then at the end, all of our energy has transformed into kinetic energy. So this tells us that we can set our potential energy at the beginning exactly equal to our kinetic energy at the end. So now we can go ahead and fill this in to solve for our velocity at the bottom. Now you might notice that we have mass on both sides of the equation, so we can go ahead and divide both sides by mass to just totally remove that from our equation. Our next step, to get v by itself, we need to undo this division by 2, so we'll multiply both sides by 2. That will cancel out this 1/2. Now the only thing left is to take the square root to undo this square. So once we do that, we'll see that our velocity equals the square root of 2 times our gravity constant, which is 9.8 meters per second squared, times the height that we're at, which is 10 meters. And when we run that through our calculator, we find that this is 14 meters per second. That's wicked fast. So why don't we take a look at the situation where there is some friction between our sled and the hill. It'll be a little more realistic. Now if we consider friction in between our sled and the hill, then what that means is friction is going to slow us down on our way. So at the bottom we will not have 14 meters per second of velocity. So what if we say that our velocity down here at the bottom is only 12 meters per second? Then what we want to find out is how much work did friction do on us. So if we draw our little bar graph for this situation, we're going to have to add a third column for the work done by friction. So at the beginning, we're still going to have all of our energy as potential energy. But what happens when there's friction in between our sled and the hill is some of this energy will be sapped away, stolen by friction, and turned into heat. So our kinetic energy will not be equal to the potential energy. Some of it has been taken over here into the work done by friction. So this time, instead of setting our potential energy at the top equal to our kinetic energy at the bottom, it has to be equal to the kinetic energy plus the work done by friction. Now for this calculation, to find the work done by friction, we are actually going to have to know our mass. So why don't we assume that our mass is 50 kilograms. Now if we do some algebra to get this by itself, all we need to do is subtract 1/2 mv squared from both sides. So that was pretty simple. I guess we can go ahead and plug in our numbers to see how much we get. And when we plug this into our calculator, we will get that the work done by friction comes out to 1300 joules, or 1.3 kilojoules of energy. Well, our initial energy, mgh, equal to 50 times 9.8 times 10, comes out to 4,900 joules, or 4.9 kilojoules. So now we can compare the work done by friction to the total amount of energy that we started with. So if we take the work done by friction divided by the total energy we started with and multiply it by 100%, we'll find that the work done by friction accounts for 26.53% of the total energy that we started with. So on the way down, our sled being in contact with the hill, it lost about a quarter of its energy just being dissipated out into heat. And that is how you can relate energy of both kinetic and potential types with work done by a non-conservative force. So if you guys found this video helpful, please be sure to like it and share it, and have a radical day.